Want to hear a paradox? Consider the distance between you and me, which is 16 feet. I want to walk over to you. Now to reach you, I decide to take my time, so I'll walk to you in successively smaller increments, where each step will cover half the distance between us until I eventually find myself at your location. My first step is 8 feet long, the first half of that 16-foot distance. Now a smaller gap remains between us, so I take another step to cover half that 8-foot distance. So I walk another 4 feet, then another 2 feet, then another 1 foot. I continue the process, brimming with confidence, knowing full well I will eventually reach you. But will I really reach you? I mean, at any given instant, if we stop the process, there is always half of some distance that remains left to be covered. The answer is actually yes. And in explaining why, we'll discover the concept of a limit. The path taken could be viewed as a function of distance depending on time. Now let's broaden this concept and focus on a function y equals f of x. The definition of a limit of a function f of x as x approaches a is we can make f of x as close to the limit L as we desire by taking x to be sufficiently near x equals a, but not equal to x equals a. We don't even care if the function exists at x equals a. What exactly do these words mean? Let's see if we can evaluate the limit of a mystery function as x approaches 3. We want to estimate the value of this function when we're really close to 3, like really close to 3. But this is the only information we have. What do you think the outputs are close to when x is near 3? Because these outputs close in on the limit. Are you thinking it could be anything? Your guess is as good as mine. So if you knew the value of the function at x equals 2.9 and x equals 3.1, well, that would help. After all, these inputs are pretty close to 3. They're only 0.1 away. Well, this still isn't really helping us estimate the value of the function near x equals 3. Let's look at the inputs even closer to x equals 3, like x equals 2.99 and x equals 3.01. Now the inputs are 0.01 away from x equals 3, and that's pretty darn close. So what do you think the outputs of the function are closing in on as x gets near 3? You're tempted to say 5. But let's see how good your intuition is. Let's look at the values of the function at x equals 2.999 and x equals 3.001, so that now we're really close to 3, 0.001 units away. It sure looks like the outputs are close to 5 as x is really close to 3. To use the language of limits, we would say numerically. We can say the limit of the function f of x as x approaches 3 is 5, because we can make f of x as close to 5 as we desire by taking x to be sufficiently near 3 but not equal to 3. We don't even care if the function exists at x equals 3. Now, because we're lazy, we don't want to write all of this out every time we evaluate limits, we use a shorthand that captures the input as we are approaching the function and the limit. Do you see a parallel here with me walking over to you? Even though half the distance remains with each successive step, I can still get as close to you as I desire by taking steps sufficiently near you, just like we could have made the outputs of our function as close to 5 as we desire by taking x sufficiently near 3. Now, will I really reach you? We don't really care about half of the infinitesimally small gaps that remain because the answer is yes. Now, my bringing with confidence is reassured. I can walk to your location, and even though you're 16 feet away, I know I can full well eventually reach you. Keep this in mind when you watch the 2 instructional videos and learn more about numerically evaluating limits and also how to evaluate them using graphs.